Yeah, hi, this is Eric Katz, instructor at Full Stack Academy. And this is going to be a lecture that's going to help us prepare for our first couple of workshops, which are going to be centered around data structures. In particular, we're going to be implementing a queue, we're going to be implementing a linked list, we're going to be implementing a hash table, and we're going to be implementing a binary search tree. And we're going to get to those things in some more detail a little bit later in this presentation. But a lot of this is going to deal with background and some computer science theory, some basic hardware information. It's not going to make you an expert on these things, but it'll give you some context to what's going on inside of the computer, how we ended up getting to where we are. I also wanted to just thank Gabe Lebec, who put together this presentation, and I'm using a lot of his work and quite a few of his words as well. So I want to thank him for that. So let's actually start out by talking a little bit about information theory and then we're going to dive into hardware a bit. So in terms of information theory, what are we looking at here? Well, doesn't really look like we're looking at much of anything, right? Not to get too philosophical, but it doesn't really mean all that much until we end up contrasting it with something else. So here we can make a distinction between two different things. And once we do that in information theory, we could sort of talk about the smallest bit of data, which would, be a true and false value, or an on and off value, or eventually what we're going to look at as bits, which is a 1 and 0 value. So we call these values true and false, and in fact, we call them Boolean data. And where do we get this word from? Well, George Boole was the inventor of Boolean algebra, where basic operations were used on Boolean data, and really it's the basis for computing. Some of these operations, the AND operator, the OR operator, the NOT operator, and when you string along enough combinations of these things, you can do some powerful computing. Some things you already know about already is that, if we say true, we know that true and false is going to be equal to false, right? Or true or false is going to be equal to true, or not true is going to be equal to false, or not false is going to be equal to true. So you really know these operations, but again, stringing enough of these things together, things can become quite powerful. So we end up moving from Boole. So here's a picture of Boole. We end up moving from him to Claude Shannon. And so Claude Shannon proved that it would be possible to use switches to solve Boolean algebra. So basically using electricity to solve Boolean algebra. And electricity was a pretty good medium for this. And here we could look at, we think about electricity, we think about on and off. Again, the whole idea of true or false, on and off. Here, if we look at the circuit on the top, right, this would approximate a AND operation, right, where both of these things have to be true in order for this to be true. And if we look at the gate on the bottom, all the way here, if we look at the one on the bottom, the circuit on the bottom, we could see that this is an OR operator, right? If any of these is true, right, we're going to end up getting current that ends up going through this. So, this is sort of the beginning, really, to the information age. But, in terms of how practical this would get, is going to be determined by, how small these switches could end up being. Right? We've all seen diagrams or, pictures of like early computers where they took up an entire room, but obviously things ended up getting miniaturized, and that ended up being very helpful. Here we have a MOSFET, a metal oxide semiconductor, and this is an Ivy Bridge transistor, which is basically the basis for an Intel chip. So you have a source, you have a drain, and you have a gate, which could basically turn these things on and off. And it was pretty much the miniaturization of all these things that really makes things practical. So here we just have an idea how the basis for all this stuff is Boolean algebra, how we could end up creating these sort of Rube Goldberg machines out of these switches. When they get small enough, things get pretty interesting. So the next thing we'll start to take a look at is really how our data ends up getting stored, and how we could sort of turn this into some meaningful information in terms of reading files and that sort of thing. So that's the next thing that we'll end up taking a look at. So now let's actually talk a little bit about storage, right, which becomes important in terms of computing. So this is actually a picture of Herman Hollerith, and just to give you a little bit of a background on it, right? In 1880, they ended up doing the census for the United States. It ended up taking 8 years. So this is in 1880. In 1889, Herman Hollerith does this thesis, which basically involves storing data inside of punch cards. And basically, you can see him feeding a punch card in here, but if you look at the punch card, right, the holes are basically are used to store data, right? This is a form of encoding, which we'll end up talking about. And just to give you an idea about what difference it ended up making, right, where the census before took 8 years in 1880, ends up taking 1 year in 1890, which was a huge savings. Ended up coming in under budget. So one thing is to sort of think about, and we'll talk a little bit more about this when we end up looking a little bit more about encoding, is the idea how there's an abstraction really where, in this case with the census, these holes are going to indicate information that would be on a census, like age, state, gender, marriage status, etc. And so in essence, these holes are going to be representing the data about a person. It's also interesting to note that this company that he ended up creating, the tabulating machine company, became pretty famous later on and ended up changing its name in 1924 to IBM. So it was kind of an interesting tidbit. Now, again, we don't end up using punch cards, right? Punch cards ended up getting replaced by magnetic tape. So it's actually a picture of Grace Hopper, who is the inventor of the compiler, and actually credited with the term debugging, where she found a moth inside one of the computers that ended up causing an errors. But really what we're looking at here is the idea where we had holes before to represent data. Here, we're actually using, on these tape drives, we're using the polarity of tiny magnets to indicate ones and zeros. And the thing that's interesting about that is that they're still used today. And one of the reasons why they're used today is that they're incredibly cheap, right? They're also incredibly slow, but I mean, sometimes when something is cheap, it sort of wins out. Now, if we'd sort of take a look at what the predecessor of these tape drives are, right? Here's a picture of the Torah scroll, which makes me think back to my bar mitzvah, but I'm not going to bore you with any stories about that. But looking at this, you could see, in fact, when they end up unrolling the scroll, they actually read this scroll through the course of a year, and there's a holiday where they're basically rewinding the scroll. So, again, this is nice that you could store this information on here, but it becomes pretty hard to search for things, right? I mean, you have to basically unwind the whole thing to get where you want to go. And again, if you wanted to sort of add something to a scroll, that becomes a little bit problematic. So just to give you a comparison, right? Let's compare this to a book, where a book allows you to open up to any page, and you could pretty much get to where you want to be. So if the scroll is analogous to the tape drive, then we could say that the hard drive is going to be analogous to a book. Now, the hard drive was actually invented in the 1950s, but it didn't become common until much later on, until the 80s. And in essence, the head moves around to get to your information the same way that your finger would be used to open up a book. If we sort of go a little bit further, we could start to think about flash memory, where it was even, it was non-mechanical, where basically, microcircuitry is used to store data in electron traps. And again, the whole idea here is that this became a little more expensive, and it actually is even there's less longevity than you would have with something like a tape drive. But again, it's pretty fast. So again, what we're talking about here is the storage of data, and we can think about data being stored. If you're sort of thinking about working at your desk, you could have files somewhere off into the side of the room, right? But anything that you're working on, you're going to want to have it close to you. So even though there's a distinction between memory and storage, right? And sometimes the line could be blurred a little bit. I don't know. Maybe today's memory might be tomorrow's storage as things get faster or that sort of thing. This is an interesting diagram because what it really tells us is that, as we move to something that's faster, the size becomes much, much smaller. So we could see that, for instance, on a tape drive, we could store a lot of information, but the amount of time that it ends up taking us to get that information is incredibly slower than it would be when something is stored in a CPU register. And again, as we sort of move from the bottom of this chart up to the top, right? We sort of think about what's under that line as being storage, in terms of it being sort of blocking, right? And it actually persists, as opposed to what's on the top, which is non-blocking, meaning we could get to it very quickly. But it's also volatile in the sense that, if the power goes off, we end up losing our data. That's why, we say that we, save early and save often. So we could also sort of make a distinction as to when we end up looking at memory about, what these various pieces are doing. And we'll look at some diagrams so you could see, what the RAM is as opposed to, moving all the way down to the register, which, it used to be not that long ago where a register was 32 bits, and see a 32-bit machine. You could even see when you download software, it tells you whether you want to have a 64-bit version or a 32-bit version. So there's not a ton that we could store there. And again, the other thing is that as we move from the bottom to the top, things get more expensive, and obviously it's going to be reverse in the other direction. So if we go and look at this, this is a picture of dynamic RAM. And what ends up happening here is that processes that we're running end up loading into dynamic RAM, so we can end up, our operating system can end up interacting with them. That's one of the reasons why you see that if you're going to upgrade a computer, one of the big bang for the bucks you could get is by replacing your RAM, right? You sort of see it kind of falls in a sweet spot over here, right, where it's fairly fast and there is a decent size of memory that it ends up having. Here we're actually looking at a chip, right? And if we sort of dive down a little bit deeper into here, there's several levels of caching where individual pieces of data that we end up using often can be put into caches. I mean, in the end, the only way that we're going to be operating on the data is for them to go from the caches up into our registers, right? Which we represented, we could show here, which is where our CPU register, where we're going to be actually operating on the data. So this just gives you an idea of memory and storage, and really how you have this trade-off. Okay, so the next thing we're going to do is we're going to talk about how we take these ones and zeros and convert them to something more meaningful. So here's a little bit of a joke slide. There are only 1-0 types of people in the world: those who understand binary and those who do not. It's like the joke about you could only understand recursion if you understand recursion. And really, there are only two type of people, right? 1, 0 is going to be 2 in binary. So you've probably seen this before, but just in case, right? When we end up looking at binary, we're using ones and zeros to represent, in this case, anything from 0 to 255. And the way to think about it is that, if we look at each of these bits, it's the position of the bits that determines the value. So even though they're ones and zeros, right, the order of magnitude of either those ones and zeros is going to be, if it's all the way on the right over here, it's going to be multiplied by 2 to the 0, which is 1. It's going to be multiplied by 2, by 4, right, by 8, by 16, by 32, by 64, and by 128. Let's just sort of remember this 32, because we'll get back to it later. So if we end up looking at this this byte, right, this 8 bits of binary data, right, we could go down and we could say, well, we've got a 64, we've got a 32, we've got a 4, and we've got a 2. And this is, if the math is correct, right, which hopefully it is, this is going to give us 102. So we've got a way, obviously, of representing decimal values. The question is, how do we turn these decimal values into, let's take the case of text. So you could sort of think about, how we might end up doing this, how we end up getting, how we end up representing characters, how we end up representing text. And we could think of a very simplistic example. My son actually stood about this the other day. He ended up writing all the letters down and putting numbers next to them, and he was spelling out some curse words, which was kind of interesting. But he would find this ring pretty cool, right? This is a decoder ring, and that's fine, right? If assuming everyone agrees on those characters, but you see we're pretty limited as to how many we could end up putting around our finger. Here we have a ring that's just dealing with uppercase English letters. So what happened, this goes back to the 1960s, and it goes back to what were teletype machines or teleprinters, and you could actually see one over here. And so basically they were transmitting data, right, with numbers. They wanted to convert numbers to letters and also to characters and that sort of thing. And the way that they did it initially was 7-bit, right? There were 7 bits that they sent over. So, in essence, they were looking at this limited set of characters that they could have, 128 characters. There's a couple of things that are kind of interesting here. One of them being that you had all these symbols and numbers before this, but you see with ASCII code 65, we have an A. So here we have the 64 bit, and we have A, and as we move over, we're going to have 1, and here we're going to have a B, and here we're going to have a C, and we move to a D. And the thing that is kind of interesting is that the lowercase numbers for ASCII actually just involve this 32 bit. So this bit at the 32 position, where if you wanted a lowercase a, instead of it being 100, it would be 110. And the same thing for B. So just kind of interesting. And again, it was designed that way, so you could convert from uppercase to lowercase. It's also the reason why in JavaScript, or it's got to be part of the reason why things end up getting sorted in the order that they do in terms of text, right? It's going to be based upon ASCII values. So this sort of works out well until different countries end up doing different types of encoding, right? We ended up doing encoding here, but different countries have other types of encoding. And really, I think the biggest issue is that there are a lot more characters than the 128 characters, or even if we, when we end up going to 8 bits, because that's how we tend to store things, we're limited to basically 255 or 256 values that we can end up representing. And so this ends up being problematic because there's languages that have a lot of other characters and there's a lot of other symbols that we want to end up representing. So what ends up happening here, and I think to some degree, this is just going to let you know, given the choice, you should probably end up using UTF-8, but let's just talk a little bit about where this ended up coming from. So really what ended up happening is that there was a standard that was invented, or a better way to say it is that people agreed on what Unicode characters were going to be. So there's this consortium that has over 100,000 different characters, and they're basically, each character corresponds to a number. Each character corresponds to a code point, right? And what's interesting is how UTF-8 is using these characters to convert them, these numbers to convert to letters. Now, the thing that's good about it is that it was backward compatible. So if you just ended up having an ASCII file would be a totally valid UTF-8 file. So, this is a ASCII value, right? So the letter 49 is going to correspond to a capital I. And, this would be, if this was a ASCII file, right, that's all you would have. So really what it ends up coming down to is that when you end up having a lot more choices for characters, you could decide, well, I'm going to do something more than 8-bit, maybe I'm going to have to do 16-bit or that sort of thing. And if you ended up doing that, sure, you could put your ASCII character in there and fill the rest of the bits with zeros. But, things were kind of problematic because if you ended up having there are systems where if you're sending over 8 zeros, it's considered a null value or a termination value. And on top of that, you have a huge memory issue. So, if ASCII fits fine into 1 byte, then, if you ended up going to Unicode and ended up using a bunch more bytes, right, you'd have these bigger files with really no reason to have those files. So ASCII was backward compatible. So ASCII would look, just like this in UTF-8. So here we're using a symbol. Now, there's basically this whole way that this stuff gets converted, but it's a little bit of an explanation here is that these 3 ones over here tell the encoding, the transformation says that we're dealing with 3 bytes here. And really what it ends up coming down to is that you start looking after, when you get to the 1 here, and what ends up counting is this 1 and 0. This 1 and 0, these are considered control characters. So in this case, you'd be counting 1, 0, 0, 1, 1, 1, 0, 1. This is another set of control characters, the 1, 0. And then you'd have 1, 0, 0, 1, 0, 0. Now, if you took this big number here and you ended up converting this to a decimal number, you wouldn't get 2764 because this is actually a hexadecimal number. If we were to go and convert this hexadecimal number, let's see if we can just find something real quick. So if we did a hexadecimal conversion, let's say hexadecimal to binary converter, and look to see if we could, for the sake of argument, we could show something kind of interesting here. So here we've got 2764, and if we go over here, we put in 2764, and we convert it, we've got this binary value, and let's just sort of move this so we can see this at the same time. And we make this a little bit smaller. And again, this is not something that you have to know, it just is maybe some interesting information. Maybe at a party you could entertain somebody with this. Let's see how we could show this. Make this a little smaller. Okay, so let's see if this works. So here, if we look at 2764, we see this binary value. And if we actually start reading over here, we could see, if I start reading my binary value, 0010, and then we go 0, 1, 1, 1, 0, 1. And then we start moving over from this direction. And I think that that's correct. And again, I could be off in my scheme, but that's generally the way that it works, where this is going to indicate that there's 3 total bytes. This 1, 0 is going to be a control character. And so basically, you're taking part of this, and part of this, and this basically converts to some big number, and that big number corresponds to a Unicode symbol. And that's basically what UTF-8 is. So Unicode is basically this consortium that is creating these code points where numbers correspond to characters, and UTF-8 is the scheme to figure out which characters that you have. So, here's another ASCII value, here's another ASCII value, and there's one on the bottom here, and this is going to be 4 bytes. So if you went and did this conversion here, you would end up seeing that this would, I don't know, let's give this a quick shot. I don't know if I'll get it to work, but let's just see. Let's see, 1F604. And convert. And we'll see. We'll just look at the first few characters here if we can do this. So here we've got 111 here, and actually maybe it's better if we move from the right to the left. So you can actually see here 0010, 000000, bunch of other zeros, 11, and then another 0, and then you could see these other ones here, right? So I don't know, there's some zeros there at the beginning that are kind of screwing me up a little bit, but you kind of get the idea. And again, it's not like you have to do this conversion, but the key thing here is that ASCII will work with UTF-8, and again, when in doubt, you should end up using UTF-8. It works pretty well. There's also something called UTF-16 that you could use, but it's really not great, and you should probably avoid using it. You could run into some compatibility issues with ASCII. So if nothing else, that just sort of shows you where that comes from. Now, we can also just talk a little bit about how images get encoded, right? So we could think about text, but images maybe even are a little bit simpler, where you basically have a red, green, and blue value, and based upon the different red, green, and blue in a pixel, right, that'll end up translating to a color, and again, that's how that image data would end up getting stored. So the next thing that we're going to take a look at is a little bit about how your code is written and how compilers work, and sort of what the difference is between the code that you write and what's actually running down in the bowels of your machine. So this part's going to be pretty quick, just to talk a little bit about how our code ends up getting compiled or it ends up getting interpreted. So in essence, we're writing this code, but that's not actually what ends up getting run, right? In the end, when we deal with computers, we're going to deal with ones and zeros. We're not writing code to actually impact specific registers, right? The code we write is an abstraction on top of that. So depending on whether you're talking about compilation or interpreting, in the end, the code that you write is going to turn into something else that is going to be able to interact with your operating system. So, for example, I mean, it is kind of important to make the distinction. There are certain languages like Java and C# or C++ where code has to be compiled first. And one of the things that happens in a compilation process is that compilation process can be a little bit slow. And one of the things that happens during compilation process is that, and this is usually the case for strongly typed languages, where if you have compilation errors, those will end up getting caught. Now that's not going to happen in JavaScript. A lot of times, you're not going to find your JavaScript compile errors until you end up going and running the program. Now, again, in programs that aren't compiled, you have source code that ends up getting interpreted. So examples of languages that end up getting interpreted would be JavaScript gets interpreted, Ruby gets interpreted, Python, I think, ends up getting interpreted. So there's again, one of the things that people will make the argument that code that gets compiled is going to be more type safe, and you'll catch your errors earlier on, and other people might argue that it sort of slows down the process a little bit more. So sort of looking at this diagram, I mean, I think sort of what it's showing is that, even though you're writing your code, you're not interacting. There's a bunch of different layers before you end up interacting with your operating system or your memory. You're not interacting with registers directly. You're writing your source code, which is either going to get compiled or interpreted, and that code is going to be making system calls to the operating system. I mean, in the end, when things are going to be accessing your hardware and devices, that's going to be machine code, which is going to be a very specific set of instructions, which is executed directly by the OS. And here's just another example of it, which is kind of a similar concept here. I think we could probably, say here that the kernel is really representing the operating system, but otherwise it's another different view of the layers that you have. So one thing that's you should sort of think about a little bit is that some languages allow you to get closer to the operating system, and sometimes that could result in an increase in speed. For instance, in C++, or I think even Objective-C, you have the ability to, the programmer is responsible for dealing with memory. And again, they might be able to get closer down to the operating system, but that doesn't come without other issues that, if you could get closer to the operating system or closer to the memory, then you might be responsible for doing more things like garbage collection and that sort of thing. So, when we specify variables in JavaScript, right, it's not like we're specifying the memory position where these variables should be. We're just setting aside some memory, and the operating system is going to take care of the rest for us. So at this point, we're going to actually go in and look at some more details of the data structures that we're going to be dealing with in the workshop. Again, everything that we looked at prior to this was just a little bit of history and just to give us a little bit of background on this stuff. But now we'll look at some data structures, and we'll talk about how we're going to implement the various data structures. Again, we're going to be looking at a queue, we're going to be looking at a linked list, we're going to be looking at a hash table, and we're going to be looking at a binary search tree. So now let's talk a little bit about the workshops that we're going to do. So basically, we're going to describe a data structure. We're going to describe a queue, write some tests for a queue, and then you're going to have to implement that structure using JavaScript. We're also going to describe a linked list, and you're going to have to implement that as well. So let's take a look a little bit at these structures. Right, so picture is worth 1,000 words. A queue is basically a line that you would see at a store where you get on the end of the line. That's called end queuing, and then once you get up to the front, you will dequeue, which is to get off the line. So it's basically a first in, first out structure. Right? We could compare that to a stack where on the left here we have a stack where the last thing that goes in is the first thing that comes out. Again, that might be valuable for some kind of call stack. And a queue where the first element that goes in is going to be the first element that goes out. So you would NQ on this end and DQ on this end, where a stack, where you're basically going to push on top of the stack and pop from the stack. So that describes these data structures, and this is another description, a little bit more of a description for a queue. So, if this, assuming they're facing in the right direction, right? If this is the first person on the line, she's going to be the first person to NQ, and she's also going to be the first person to DQ, right? You can't cut the line. So you're going to have to implement that structure with JavaScript. And the only thing is you're not allowed to use, internally you could use an array, but you're not allowed to use any of the array methods like push and pop and that sort of thing. You're going to have some way of keeping track of, what the end of the line is, so you could put something on the end, and what the beginning of the line is, so you could pull something off the top. And also you want to have to have an idea of, how many people are online. That's the other thing that's pretty important. You can implement some of these other methods, although I don't think we have tests for them. So let's talk about what a linked list is. So the big difference between a queue and a linked list is that usually you're going to end up using nodes for a linked list, and we're going to talk about linked lists that are singly linked and doubly linked. With a singly linked list, you can only go in one direction. With doubly linked list, you could go in either direction. So again, let's look at a diagram of this. So here we have an example where we have an empty linked list. We just have this head property. It's not pointing to anything. And this is going to be unidirectional, right? It's only going to go in one direction. So here we end up creating this node with a value of Omri, and we end up pointing the head to this node. And if we were to go and add Joe, we would create a node for Joe. Now, right now, they're not connected to each other, but then we could set the next property of the node with the value Omri, and we could point that to Joe. Now, this is showing that this is the tail, but it could be that you don't necessarily have a pointer to the tail. It could be that the head is the only pointer that you have, in which case, when you're traversing this, you're going from the head to next, and then you have nothing, and then you have the tail. So one of the things that you can do with a linked list is you can add items in between, and the way that you do that is, again, you'd create a node with this value of Gabe, and if you wanted to insert him after Omri, you would have Omri's next property point to Gabriel. But you don't want to lose Joe, so you want to make sure that Gabriel's next property ends up pointing to Joe. So you can see it's fairly easy to insert elements here. And again, one of the things here that's important for a linked list is that they don't necessarily have to be, and they're usually not, in contiguous memory, right? To some degree, that could be an advantage because you don't have to set up this block to put items into the linked list. You also have a disadvantage in terms of getting at the items. Again, assuming you have a long list and you wanted to find a particular node, you would have to keep on traversing the node to find it. So, let's say you were going to find Joe, you'd have to start at the head, go to Omri, to go to Gabriel, to go to Joe. I just wanted to do a little bit of a comparison here to show you the difference between an array and a linked list. So, in an array in its pure form, you're basically setting up this contiguous block of memory for elements in your array, and each of the elements takes up a distinct amount of memory. So the advantage to an array is that the elements are ordered. You could get to any of the elements by the order. So again, if you know what the size of these blocks are, you know that you're going for the second element, right? You start at this memory position, and you go to this memory position, and you read this, and you're able to find your element pretty easily. As opposed to, again, going through a linked list, if you want to get the fourth element, you don't know from a memory perspective exactly where it is, so you literally have to, start at the head, go to the next one, go to the next one, go to the next one, and then you could end up, getting at what you're looking for. So that's a big distinction, and we'll compare these two things in a little bit. The other thing that I just want you to see here, and this was sort of described before, that if you have an array and you want to add elements to the array, it's more complicated than doing it for a linked list. So assuming that there's an array up top, you have these elements here, and let's say that you wanted to insert this too. Like a linked list, you could do it pretty easily, right? We saw that you can come in here and you can, create Gabriel and then connect these things, okay, pretty easily. With an array, when you're attempting to do that, here you'd actually have to move all of these elements. You have to be sort of pretty careful the way that you move them. I mean, if you just move 3 to this position, you'd be overriding 5. So, here you basically have to just shift things over, right? So you're shifting the 9, you're shifting the 5, you're shifting the 3, and then you have a space and you end up adding the 2. So the array is going to be pretty fast in terms of accessing things in the array, but it's going to be pretty slow if you want to start inserting things at different positions inside the array. So that's a distinction that you want to make. So again, this is just a comparison between those data structures. So our linked list here, another thing that we could do is, I mentioned before, this could be bidirectional. So not only could we have a head but we could also have a tail. And so we could start at the back and we could work forwards. We could start at the head and we could work back. So this is going, the head is in front, so this is next, and this is next. Again, however you want to implement it. We're going to end up implementing methods on our linked list so that we're going to be able to add to the head, remove from the head, add to the tail, remove from the tail, and deal with some end cases where you're removing the last element or you're inserting into an empty linked list and that sort of thing. So that's generally what the structure is. So this is something that I mentioned before. If you're trying to get inside of a linked list, if you're trying to reach an element, you have to crawl, right? Because it's not going to be contiguous. With an array, it's constant time. You know the size of each element in the array, so it's pretty easy to get to any position in the array. If you want to insert it to a linked list, it's fast, right? Because you could just change a couple of pointers. You have things by reference. In an array, it's tricky. You've got to move the following elements, which we saw before. If you want to add an element to a linked list or an array, it's pretty fast. You can just add it to the end. In terms of space, the linked list is going to take up a little bit more room because you're going to have pointers to the previous and the next elements. In terms of size, a linked list could grow as much as you want it. You're basically just adding pointers. Again, things don't have to be contiguous. With the array, again, it's a little bit different because you're reserving the space. And I think internally with JavaScript actually does this. But again, when your array ends up getting too big, it finds more memory and moves things over. Again, it's not necessarily that you have to overthink these things. Some of this is just so you have some knowledge of what the advantage is to these different structures are. And like I said, part of it is understanding object orientation a little bit more in JavaScript. The other thing is that these work out pretty well for job interviews. And also, last but not least, the other point that I wanted to make in terms of where things are on the disk, not likely that your linked list is going to have things together because they don't have to be together, but it's likely with an array that things are going to be close together because, again, you're setting up contiguous memory, so you could end up getting at the things that you're looking for inside the array. So what I'm going to end up doing on Tuesday is I'm going to put you guys in pairs, and we're gonna end up starting with the DataStructuresPart1. We're going to do the workshop. You're going to work on it, I think, a little bit more on Wednesday. And then we're going to start looking at 2 other data structures. So we'll have a short lecture that describes both hash tables and B trees. So we will binary search trees. So we'll end up talking about that as well, and then we'll do our data structures part 2 workshop. So that's about it. Thank you.